Working toward creating sophisticated structures in the modern era of organic synthesis relies upon taking advantage of purposeful molecules to enhance efficiency and productivity of the approach. Indeed, the ultimate ambition of every synthetic chemist is designing groundbreaking strategies that can shorten the steps required for synthesizing a target, thereby saving both time and money. With this consideration in mind, designing the purposeful molecules is of prominent importance. Purposeful molecules refer to the compounds that are readily accessible and are bench stable. Moreover, the central reason that they are considered purposeful is that they are multifunctional. In other words, different functional groups, each with its own characteristic features, coexist within the same molecule. This coexistence offers substantial benefits when reacting with a variety of building blocks such as allenes, double bonds, dipole units, small rings, and similar structural motifs. As a result, the presence of different functional groups enables the molecule to engage in various modes of action, including nucleophilic attack, electrophilic attack, ring opening, unusual rearrangement, and etc. Ultimately, this diversity in reactivity leads to the construction of complex scaffolds. Now let's explore how this process works in practice. Ethynylethylene carbonates fit perfectly the definition of purposeful molecules. What makes this compound truly fascinating is the different mode of reactivity. Correspondingly, they consist of a cyclic anhydride, which can undergo ring expansion, leading to the rupture of a carbon dioxide. Moreover, acetylene functional group undergoes nucleophilic attack as an acceptor, and as a donor group, it can attack to other nucleophiles. Furthermore, depending on what starting materials are utilized to synthesize this molecule, the oxygen atom can be replaced with nitrogen, which adds to its diversity and modes of action. Thus, there is no wonder why this structure has caught the attention of synthetic chemists in the recent years. Now let's analyze the synthesis route. In the first step, alpha bromoketone is converted to alpha hydroxyketone. Then the acetylene is installed in the molecule by Grignard reaction. Finally, exposure to CDI affords the final product. Mechanistically, first hydroxy group attacks to the EDI, then second hydroxy group attacks to the carbonyl group, leading to the target molecule. Contiguous carbon stereogenic centers are a common feature of complex natural products and drugs. For instance, tricodeine, anguidine, and buprenorphine indicate this unique pattern. In this motif, the orientation of substituents at carbon stereocenters has an impact on shape of many structurally complex scaffolds, which are closely related to properties of organic molecules. Creating molecules having contiguous carbon stereogenic centers constitutes a daunting challenge, in particular when they are quaternary centers. The central reason is the steric hindrance, which substantially increases and imposes remarkable difficulties on the synthesis. In 2023, Ming Group represented a cascade reaction to produce substituted spirolactone skeleton containing two contiguous quaternary carbon stereogenic centers. They used ethynylethylene carbonate as electrophile and indinone-based nucleophile. Furthermore, using of chiral diphenylethylene as a ligand led to the high stereoselectivity, which adds to the value of the synthesis route. Now let's walk through the mechanism of the cascade. First of all, acetylene should be activated for initiating the cascade. For this purpose, triethylamine as a base abstracts a hydrogen from the terminal alkene, and the activation process is completed by attaching the copper ligand to the alkene. In this step of the cascade, CO2 is released from the molecule in the reaction condition due to adjacency of triple bond and cyclic anhydride by an addition-elimination mechanism. In other words, the triple bond assists the releasing of CO2. This is called neighboring group participation. Releasing of CO2 is a powerful driving force for this reaction, so this step is irreversible. Notice that this carbon atom is attached to a phenyl ring, so it has a carbocation character, which can be stabilized by resonance. Thus, indinon as a nucleophile attacks this carbon atom. In the final step of the cascade, the hydroxy group attacks the ester group of the indinon moiety, and ethanol leaves the molecule by addition-elimination mechanism. Now let's explore the origin of enantioselectivity in this reaction. Imagine this plane is attacked by a nucleophile. As you see, it can attack from below and above the plane with equal possibility. So this imaginary reaction is not enantioselective. If we want to carry out the reaction in an enantioselective fashion, we should create a bias in the system in such a way that one face of the plane is attacked more than other face. If the nucleophile differentiates between two faces of the plane, we achieve enantioselectivity in the reaction. Now look at this transition state in which the nucleophile attacks the sp2 carbon atom. As you see, the bulky sulfonyl group hinders the attack of the nucleophile on this face of the molecule due to steric hindrance. As a consequence, this transition state is attacked from the outer face, where there is more space for nucleophile to approach. It's a good example of how synthetic chemists design an enantioselective reaction, where using an appropriate ligand plays a crucial role.